In this final section of chapter 3, we shall see an interesting class of functions, namely so-called trigonometric functions. These are basically the functions sine, cosine, and later on also the tangent. You've probably all encountered them in high school in connection to Euclidean geometry. And yeah, we will now develop them in our really rigorous axiomatic framework. And you might not recognize them at first, but we shall see like how our definition is in line with what you know before. I've prepared a bit, so this is basically summarizing a bit of high school mathematics. Namely, sine and cosine there occur when you study right-angled triangles. I've drawn a right-angled triangle here, so this is a right angle here. I don't know if this notation for a right angle, so this quarter circle and a dot, if this is common in other countries as well, I'm not so sure, but this is a right angle. So, and we have an angle alpha here in this corner of the triangle at this point, which we want to study. So, with respect to this angle, first of all, the line segment opposite of the right angle is called the hypotenuse. This one here, the line segment opposite, the side of the triangle which is opposite of this angle here is just called opposite, and this here we call adjacent. In German it would be Gegenkathete, Ankathete, and Hypotenuse, but anyway. So this is the opposite, this is the adjacent, and with these segments, with these lengths of these lines of the triangle, we can then formulate sine and cosine. Namely, the sine was then in high school defined as the length of the opposite divided by the length of the hypotenuse. Similarly, cosine is defined as the length of the adjacent divided by the length of the hypotenuse. And actually you probably haven't proven this in high school or something, one can see that this really only depends on the angle and not kind of on the size or the position of the triangle. I mean, we could rotate everything, or we can rescale it and make it bigger or smaller, preserving the angle. Or we can shift it or something, and then actually you can also show by elementary geometry that this really only depends on the angle itself and not on the precise position of the scale. Okay, so this is what you got from high school. Now let me define cosine and sine in our framework very rigorously, because this is just with respect to triangles, and this definition at first sight doesn't involve triangles at all. The cosine as a function from R to R is defined as, so we write this just as cos x, we leave out mostly the parentheses, this is quite common notation. This is just defined as the real part of the complex number e to the power of ix. So x of ix, this is the cosine function. And the sine function, also a function from R to R, is defined by sine x as the imaginary part of the complex number e to the power of ix. So this is the sine function. Whoops. Okay, I guess now you all have the same question on your mind. What? This doesn't look like it's connected to triangles at all. So this is just rigorously defined. I mean, we've talked about the exponential map before and quite in detail, so we know a lot about it. So this is just some complex number, and we have some real imaginary part. I mean, okay, these are real numbers, these functions are well defined, but what on earth do they have to do with triangles? Let me give you a drawing that might help you. So the connection of this to triangles. So we need to discuss this point e to the ix, and let us first think about this point. So let this be the complex plane. We've seen in section 2.5, basically one of the first properties of the exponential series that I've shown you, that e to I times a real number, that this has always absolute value 1. Geometrically, this means that, I mean, absolute value 1, all points of absolute value 1, these are basically the points on the unit circle here. So the circle which goes here through 1, 1, so this is the real axis, this is the imaginary axis. So this would be I here, this point. Oh yeah, okay, let me draw it like this. So here we would have minus 1 and here we would have minus I. So we need the circle. It's probably nowhere close to a circle the way I'm drawing it. Okay, move this point a little. Okay, this is supposed to be a circle. Now, the point e to the ix is somewhere on there, and assume that is of the following form, that it's somewhere here. Assume this here is our point e to the ix. Okay, what does this have to do with right-angled triangles? I will show you. First of all, let me draw the connection, so here in 0 we have the origin. Okay, so let us draw the connection line here. Okay, this line here has obviously length 1 because this is on the circle of radius 1. So now we draw 2 more lines. First of all, we draw the vertical line which goes down to the axis here. Okay, if I have an audience, if I had an audience, I would now ask what's the length of this line. This is easy to see because here, this number that is on this height here, this is the imaginary part of e to the ix, just by definition of these coordinates. So this goes from 0 to there, so the length of this is, so this has length 1, let me just draw it like this. This has length im e to the ix. So this here, this is the value, the imaginary part of e to the ix. And now let's draw a third line, and then we have our triangle, namely this one. This is just a segment of the x-axis. And if we take a look at where this point is, this is just, I mean, here by real and imaginary part as coordinates, this is simply the real part of e to the ix. So the length of this line segment here is also the real part of e to the ix. And now we've got our right-angled triangle, because this is obviously a right angle, if this is vertical, horizontal. Now, we take a look now at this angle here. So let's call this angle x. We will see that this then works out. Namely, here in this case, if we now take this angle x in the geometric definition, if we take the sine and the cosine, so the sine of x, sorry, I can leave a parenthesis here, sine of x, so it would be the length of the opposite, which we have clarified is the imaginary part of e to the ix, divided by the length of the hypotenuse, that's this line here, this has length 1. So this is really im of e to the ix, and similar for cosine. The cosine of x is the length of the adjacent, which we have established as real part of e to the ix, divided by the length of the hypotenuse, which is 1. So this really gives the real part of e to the ix. So, comparing with our definition, this coincides. So this is really a special case of the geometric definition, actually. And now, this is, of course, for a special class of triangles, namely those which can be obtained like this. So we have one point is here. So the corner points, one of them is in 0, one lies on the unit circle, and the other one here. But you can see that basically every triangle can be rotated to be not only rotated, rescaled, or shifted to get some triangle like this. And we've just discussed that this, this definition really kind of assumes that the angle, so the sine and cosine are invariant under shifts, rotations, rescaling, and so on. And so we can just take an arbitrary triangle, put it into a triangle like this, and then take our new definition and get the old definition back. So this really, of course, you would need to prove that this makes sense, so that kind of if you transform it into such a triangle, that if you have 2 different ways of transforming it, you would get the same values and so on. So you need to check that this is well defined, but this is kind of where it coincides with the geometry. So yeah, I've written a bit of this in the lecture notes, so there I kind of wanted to try to avoid a drawing, so I basically wrote a lengthy text, which is a bit tedious maybe, but you can have a look. So there I explained it in written down, so I won't write anything more here. But this is the idea. This is how we get to sine and cosine, by taking the unit circle here and the complex numbers. So of course all the time identifying C with a plane and with triangles in a plane as triangles in C and so on, and then we will get this definition back. Okay, and for the moment you just have to believe me that every triangle can be rotated, rescaled, and shifted, so to get to such a nice triangle. Okay, so but this is kind of so don't be irritated by this definition here, because this is really it goes back to this when you kind of remove all the analysis here and go back to the geometric viewpoint, and you really obtain this. Okay, so now this is also a nice interpretation, because we now see that e to the ix is the number here, such that this angle is just x. So this is also a nice interpretation of this one. Okay. First of all, by definition, let me just add one more equation. Euler's formula holds. Usually, I mean, this is not a fancy formula now because it's immediately from the definition, but Euler first derived this with kind of from more geometric definitions of sine and cosine. So this was actually a big theorem. Namely, by definition, it holds that e to the ix is the same as the cosine of x plus I times the sine of x. So this is how we decompose this as real and imaginary part. This is a very important equation, so this is basically also how you can memorize the definitions here. If you memorize just this equation, you've got both in one. But this is Euler's formula, very famous formula. Okay, I want to derive some properties of sine and cosine, and we will see that basically the geometric properties of sine and cosine that you usually see in high school, that we can basically derive all of them using our new, admittedly a bit strange looking definitions. Okay, first of all, some shorthand notation that I will use from now on. Namely, one puts sine to the power of n of x. This is just short for sine x to the power of n, and same for cosine. Cos n of x is given as the cosine of x to the power of n, and this for all x in R, n in n. Okay, this is just notation. Now, I've put the most basic properties all in one big theorem, and I think most of these properties you would already, if I would kind of now ask you to write down everything you need to know about sine and cosine, I think you would come up with quite some of them, but we shall see. Okay, first of all, as functions, sine and cosine, as functions from R to R, both are continuous. Okay, this is good news. B, there are interesting formulas for cosine and sine, namely the cosine of x is the same as e to the ix plus e to the minus ix divided by 2. Okay, this is something you've probably not seen in high school, but yeah. The sine of x has a similar formula. This is e to the ix minus e to the minus ix divided by 2I. Okay, so in particular, these two really are real numbers, which is obvious, which is not obvious at the moment, but we shall see. C, this is something you know from high school, I assume. Cosine squared of x plus sine squared of x is equal to 1 for all x in R. Okay. D, and that's basically a corollary of this one. The absolute value of the sine of x is always less than or equal to 1, same as the absolute value of the cosine of x for all x in R. And finally, a symmetry property. E, namely the cosine of minus x is the cosine of x, and the sine of minus x is minus the sine of x for all x in R. You probably all now have the graphs of sine and cosine on your mind, but we shall, and where you can basically see this geometrically, but we shall prove this now very formally. Okay, so much for that. So let's prove these properties. So first of all, part A is almost obvious, given what we've seen already. This follows from theorem 3(5)d. Okay, what does this theorem say? This says that if we have a continuous function, then the real part and the imaginary, continuous function with complex values, the real part and the imaginary part of these are always, as functions continuous as well. And we've seen that the exponential function is continuous, so if we have e to the ix, just multiplying this with a constant doesn't change, so e to the ix is still continuous. This is the power series which is continuous, and so the real parts and imaginary parts are continuous, which says this theorem. So this and the continuity of exp. Okay, part B, these strange looking formulas, and we have also, basically we have already seen them a long time ago. Namely, we've seen them in theorem, what was it? 299, sorry, no, that was the other one. 170. In chapter 1, just some basic properties of complex numbers. There we've seen that the real part of a complex number z is z plus its conjugate z bar divided by 2, and the imaginary part is z minus z conjugate divided by 2i. Okay, this was part of, for all complex numbers z, so it was theorem 170. I hope you still have this in mind. Okay, now, here we don't have any conjugation, but we have minus there. But this is something which is easy to see, namely e to the ix conjugate. There we've seen how the exponential function behaves. This was theorem 299 G. So that the conjugate of an exponential function is the same as the exponential function of the conjugate. So this is e to the ix, and now ix conjugate, and since x is a real number, this is purely imaginary, and so this just becomes minus ix by definition of conjugation. And so the claim follows. If we just insert here e to the ix or there, and then we get the two formulas here. So since this is, the equations follow. Okay, now for C, this quadratic equation. This is something you can beautifully see on with triangles and so on, but there's also proof with using just our definition, namely, again by theorem 299. No, this is now G. This was not G. Sorry, I've misread my notes. Sorry, this was just somewhere in 299 we saw that the conjugate of x is x of the conjugate. Here is now part G, namely we've seen what I've already mentioned before, that 1 is the absolute value of e to the power of ix when I is a real number. And then, of course, also the square of this is a real number. But by construction, the square of the absolute value is the same as the sum of the square of the real part plus the sum of the imaginary part. This is some elementary property, how basically that's the definition of complex value, absolute value for complex numbers. Okay, so we've got this, and now this is just the definition. This is cosine squared of x plus sine squared of x, and here we go. This was what we needed to show. Okay, D. Oops, now I have to handle the boards here. This now follows directly from this, because these are two non-negative numbers, so they together sum up to 1. So since they're both non-negative, none of these can be bigger than 1. And if this square is smaller than or equal to 1, this is the same than saying that the absolute value is smaller than or equal to 1. So this just follows from C. Okay, and finally part E. So this symmetry property, this basically just follows if we just insert minus x into these formulas. Because here we would get, e to the I minus, or minus ix, and here we would get minus minus, so plus. So this would be the same thing again. And if you would insert this here, we would just have a change in sign because of this, this sign there in the numerator. So this just directly follows from B. Just insert these equations and you get the result, follows from B. And we're done. So as you see, there's a lot of elementary properties that can be now derived quite easily with our fancy new definition of sine and cosine. Okay, we shall see some more, but now I have to erase first. The next theorem contains two equations that some of you might already have seen in high school, namely the angle sum identities. These are quite complicated looking equations, but it turned out with our new definitions of sine and cosine, the proofs are surprisingly simple. Namely, theorem 378. So the angle sum identities. Oops. Okay, so we have two real numbers, x and y. Then there are formulas for the sums of the arguments of cosine and sine. First of all, the cosine of x plus y is the same as cosine of x times cosine of y minus the sine of x times the sine of y. And an analogous formula for the sine of x plus y, this is the same as sine x times cos y plus cos x times sine y. Whoops. Okay, these two identities hold. So here we've got always cos cos, sine sine, and a minus in between. Here we have sine cos, cos sine, and plus in between. So how do these equations arise? This is now very simple because these two are real and imaginary part of a complex number, namely of the complex number e of I times x plus y. Okay, with this number we can now compute. This is namely the same as e to the ix times e to the iy, just by this miracle equation of the, this was the equation always called e, the functional equation, so to say, for the exponential function. So this is just, this law holds. And if we now use Euler's formulas, so the Euler's formula, this means that here on the left-hand side, this is just cosine of x plus y plus I times sine of x plus y. This is the same as now inserting here cosine x plus I sine x multiplied with cosine of y plus I sine y. So now, these are two complex numbers which we multiply, so there we use the definition of multiplication. So first this with this, so cos x cos y. Then minus these two here, so the product of these two, minus sine x sine y plus I times, and now we get this one with this and the other two, so this is sine of x cosine of y plus cosine of x sine y, sorry for squeezing. And if we now compare real and imaginary part, these are just two complex numbers which we compare, so the real parts are the same and the imaginary parts are the same. And the real parts give the first equation, the imaginary parts give the second. Done. So comparing real and imaginary parts shows the claim. These formulas are a bit hard to memorize in the beginning, but they are sometimes really useful when you want to make some elegant computations. Okay, oh shit, I've forgotten. Oh, sorry, I've forgotten something. Namely, I want to add a special case of this. Maybe I'll do this right now. So, what special case what we get is when we take x to be equal to y. So in particular, if we take x to be equal to y, then we get the cosine of 2x is the same as the cosine of x squared minus the sine of x squared. And if we now use this identity that sine squared plus cosine squared is equal to 1, sine squared is the same as 1 minus cosine squared. And if we put this in here, we get 2 cosine squared x minus 1. So this is what happens when we kind of double the angle. And the same for, we get a similar formula for the sine of 2x. Then we see that kind of you have twice the same summand there. So this is 2 sine x cosine x. So these are the special cases that are also really useful sometimes. Okay, so kind of we can conclude from a bigger angle, we can conclude results about a bigger angle when we know something about the smaller angle. So this is what this is the philosophy behind this. Okay, so another theorem that we get, namely we have defined now sine and cosine by the exponential function. And the exponential function is by construction a power series. So this then shows that we also can display cosine and sine as power series, namely as the following. The cosine of x is the same as the sum from k equal to 0 going to infinity of minus 1 to the power of k, x to the power of 2k divided by 2k factorial. Okay, we shall see how this, where this comes from, but I want to just write down the first summands. So the first one would be k equal to 0. There we get that x to the 0, and here 0 faculty, nothing in between. So this is just 1. For the next, for k equal to 1, we get a minus sign. Here we get x squared, and here we get 2 factorial. So this is x squared divided by 2. And as a next step, so for k equal to 2, we again get a plus sign, and here we get for k equal to 2 x the power of 4 and divided by 4 factorial, and so on and so on. The next would be a minus sign again, and so on. Now for the sine. The series representation looks quite similar. This is the sine, the sum from k from 0 to infinity minus 1 to the power of k, and now we take only the odd powers, x to the 2k plus 1 divided by 2k plus 1 factorial. And if we write down here the first terms of the sum, the first one would be simply x. This is just x divided by 1 factorial, which is 1. The next one is minus x to the 3 divided by 3 factorial, which would be 6, but anyway. The next one would be again a plus, and then we would get x to the 5 divided by 5 factorial, then a minus, and so on. So this is how we can compute them. Okay, and also the series converge absolutely. For all x in R. Okay. So how to see this, and this is also not too hard. Let's write down this exponential series that defines those two quantities, sine and cosine. By definition, e to the power of ix, so this is x of ix, and this is now the sum n from 0 to infinity, ix to the power of n divided by n factorial, and this is of course the same if I just multiply this out here in the numerator. This is the sum from 0 to infinity of I to the power of n, x to the power of n divided by n factorial. Okay, so yeah, here we, so this is just a general thing. And now we have to decide what is the real part and what is the imaginary part of this series. So this, of course, since x is a real number, this only depends on these powers here, I to the power of n. And about these numbers, we know a similar thing, namely for each, as a simple thing, for each k in n0, we get the following, I to the power of 2k. So by the power laws, this is the same as I squared to the power of k, and I squared is minus 1. So this is minus 1 to the k. In particular, I to an even exponent, the power of I here, is a real number. So if we see, if we just take at even exponents here, these are real numbers. So all the even exponents are part of the real part. Now, for the odd exponents, so if there's an I to something odd, this is, we can just pull out one copy of I, so then we have I times I to an even power, so something real, which means that the odd exponents here all belong to the imaginary part. And so now we know how to split down into, how to split this series into real and imaginary parts. Hence, split e to the power of ix into real and imaginary parts. Namely, e to the ix is now, so the real part were the even exponents. This means the sum k from 0 to infinity, I to the power of 2k, x to the power of 2k divided by 2k factorial. Plus, and now we have the odd ones, and here I just want to have the 2k plus 1. I put out one copy of I, as I just said. Then we get here the sum of I to the 2k, x to the 2k, and 2k plus 1, sorry, and here we have 2k plus 1 factorial, simply by just putting one copy of I outside of that. So, this is now, this is a real number and this is a real number, and just something, beware, you cannot always kind of decompose a series like this, so kind of to put them into different summits. This is a topic I've skipped in this lecture, but here keep in mind that this is only possible since this is real, this is imaginary, and so we can really, there we always automatically have a splitting. Okay, so now this is what we have computed, these powers of I, so this is the same as the sum from k of 0 to infinity minus 1 to the power of k here, x to the 2k divided by 2k factorial, and here we get I times sum from k from 0 to infinity minus 1 to the power of k, x to the power of 2k plus 1 divided by 2k plus 1 factorial. And if you now take a look at the definition of sine and cosine, which are just real and imaginary parts of this shows the claim. Because this is precisely the series I've claimed there. Okay, fine. So we have a power series representation of sine and cosine. So now what? What's so interesting about these things? The interesting thing always about writing something as a power series, as is the case here, it's basically a nice way, or it gives you some ways of kind of computing something complicated by similar terms, or kind of to approximate something complicated. We here see the sine and cosine in general are of course a complicated definition. Here on the right hand side, we could just have the idea of not going to infinity, but just going to some index n. So just take a finite sum here. Then we have a polynomial. And polynomials are good. Polynomials just consist of multiplication and addition, and this is something you can feed a computer with. A computer can compute these things easily, while some very abstract indirect definition, this is of course very hard to compute. So here we can approximate sine and cosine by polynomials, and so kind of really approximate these complicated functions by simple functions. We will talk about this later more in the next chapter, how to do these things, but this is kind of a way of kind of approximating these two functions here by just taking the summands here. But of course, something we need to check for this, I mean, we of course see these summands here. For large numbers of x, they become very, very big. So these can be approximated only there when the kind of the sums that are to come are quite small. And small, I mean that this is the case if we kind of are with x close to 0. So this is kind of the way of, so then of course if we're close to 0 and x is a very small number, then these summands here become smaller and smaller and smaller. And so this can give us an idea of how to approximate these functions somewhere close to 0 by some nicer, simpler functions. And this is what I want to summarize in the next theorem. And so there I can basically make an estimate, like if I only take the first n summands here of this sum, what is with the rest? How big can the rest be? So this is something we need to know to make practical computations. Yep, I just realized, sorry, something I forgot to mention. I've forgotten to mention a part of this, how to prove part of this statement. I've claimed also that these series converge absolutely. This, of course, follows since e to the power of ix, this converges absolutely. This is kind of a property of exponential series. So this is something, absolute convergence follows from the absolute convergence of e to the ix. Sorry about that. Okay, but now back to these series here, and this is now a theorem I don't want to prove, but I just want to give you here the main idea, what's kind of how to use this previous theorem. Namely, for all n and n0, x and r. So if we take the cosine of x and approximate this by the first n summands of this series that I've just derived. So we take the sum, or n plus 1, sorry, so we go from 0 to n, and we take the sum minus 1 to the k, x to the power of 2k divided by 2k factorial. So we get some remainder term, which I will call rn of x. No, sorry, I want to just move the index. So the next thing, so this goes up to the power of x to the 2n. So the next thing would be a 2n plus 2, and this is why I call this the 2n plus 2 remainder. So this is basically a series where all summands of this series are polynomials and x of index 2n plus 2 are bigger. So this is of course something, and so far I haven't said anything. This is just basically a definition of these remainders. If I can do the same with a sine function to go from x to the 2k plus 1 divided by 2k plus 1 factorial. Now the remainder would be r2n plus 3 of x, because this would kind of start with a polynomial with exponent 2n plus 3. That's why I called it like this. And now the theorem says that for each of these remainder terms, if they have some index m, so if m is the function here, then the absolute value of this remainder, this is what we want to have as this should be small. This is what we wish. And indeed it is the case, namely you can guess, or you can estimate that this is smaller than or equal to the absolute value of x to the power of m divided by m, as long as the absolute value of x is smaller than m plus 1. And this for all m bigger than or equal to 2. So this shows us kind of how the remainder is. So we have, the idea is kind of, we have a complicated function is a nice polynomial plus some rubbish, and this rubbish here is very small. So kind of if we really want to compute something, or if you want to compute the cosine up to near 0 up to some digits, we can kind of estimate like if this becomes very small, you can kind of check, okay, this only changes things in the 4th digits or something, if this is like smaller than 10 to the minus 4 or something. So here we can kind of make estimates about really approximating functions nicely. Right, so this is the idea here. So the proof of this I won't do here, I just write it down in the lecture notes for completeness. But that's kind of the idea behind these, why these power series representations have are of importance here in this setting. Okay, I will now compute a nice limit using these representations after erasing the board.